Physics means everything to the universe. Without the laws of physics, nothing would work the way it should and everything would fall into chaos. Luckily for us, everything is the way it should in the universe, and the laws of physics rule over how everything works with an iron fist. But an even deeper set notion is to make all that complexity and detail compress into a single, unified, single explanation. Enter string theory, the idea that chases at the coattails of physics trying desperately to make sense of the immensely complicated rules that make up everything. What does string theory prove? And better yet, what is it and how does it work? Well, despite my knowing very little formally about physics, we're going to tackle that monster of a question on this episode of Stuff You've Probably Wondered. In order to properly explain how string theory works, we'll have to break it down to make it easier to understand. So let's take a look at my interpretation of how it all works in 3 separate parts. Part 1. The background. If we really want to understand how string theory works as a whole, we'll have to go back to where it all really started, to Sir Isaac Newton, who developed calculus to help him develop his laws of motion among many other understandings of the world. Calculus is a high level of math that, to put it very simply, describes how things change. So when these laws were created, the general public soon came to realize that nature wasn't quite as simple as everyone thought. These first laws of physics, however, would be enveloped in a larger theory that would develop over the next century or so. Classical field theory is an all-encompassing theory that explains how fields, which are basically grids of numbers representing points in space and time, interact with each other. The electromagnetic field, for example, is a field that contains properties of light, color, electricity, and magnetism. And this field was studied very thoroughly by early physicists, so we know how anything electromagnetic interacts with just about anything else. How the magnetic field of the Earth interacts with incoming objects and light from the sun, for example. So by the 20th century, scientists were pretty sure they had figured out nature's clever ploy to confuse us with intricate details. However, all that changed when the electron was discovered by a multitude of different physicists and added to atomic theory as a negatively charged particle that orbited the atom's nucleus. Of course, this posed a small problem. Atoms were named as such because they were supposed to be the smallest thing in existence, and you couldn't split it into smaller pieces no matter how hard you tried. If these smaller things existed inside atoms, did they have stuff inside them too? To make sure you're all still with me, let's summarize what we know so far. Calculus helped us understand gravity and the laws of motion, which led to classical field theory, which we thought we knew about until smaller particles were discovered. Good so far? Okay, then let's move on to the more modern era. Ever since the electron's existence came into public knowledge, it was really all downhill from there for atomic theory. It turned out there were a lot of particles out there floating around in this cosmic microcosm, or to be more accurate, the picocosm. Because of this, the next stage of physics to be developed was particle physics and quantum mechanics. Particle physics obviously deals with the rules governing particles that make up everything, but quantum mechanics are also involved. The world of quantum stuff is a little hard to understand because before we observed particles like electrons and their strange properties, we thought everything had a perfect quantifiable truth to it. However, quantum things like electrons or photons break that mold. A famous experiment that involves electrons being fired out of a cannon onto a surface has one outcome when not observed, and a different when observed. You see, the quantum world is based off 2 outcomes occurring at once, but only one actually shows up when observed. At the heart of particle physics is this chart of fundamental particles. These 17 little bits of stuff govern everything that occurs in the universe and is split into 2 categories. One of these is the fermions, which contain quarks, the quantum particles inside protons and neutrons, and electrons and neutrinos, and bosons, which are particles that govern forces like photons for the electromagnetic force, and gravitons for gravity. Now is where the fundamental forces, electromagnetic, gravity, strong, and weak, come into play. I'd like to explain those in details, but we need to move on. With the theory of all these bits of stuff and quantum nonsense, the earlier mentioned classical field theory became the quantum field theory. In this way of thinking, we consider fields not as points on a grid, but excited states of matter which jiggle around to create various fields. This was a great adaptation to the modern way of thinking about physics, but it had a few problems. The first was that QFT tried to connect the physical with the quantum, but the theories of general relativity and special relativity follow completely different rules, where matter behaves differently depending on if they're physical or quantum. The other problem is with spin. Now, the spin of a particle is not the same spin as a top or a planet, but a far more complicated aspect in which certain particles move in a specific pattern about other particles, for example, an electron around a nucleus. Quantum field theory was supposed to make all these puzzle pieces fit together. The only problem was that the pieces were from different puzzles. Before we move on to part 2, let's review real quick. Physics tried to unlock the secrets of how stuff worked, but thanks to the discovery of nanoscopic particles, we need to rethink how we looked at physics. And when even the rules of particle and quantum physics didn't agree, we had to change our view again. What we needed was a universal, single, simple theory of how it all fit together. And this is where string theory comes in. Part 2. If the string fits. String theory was initially meant to connect particles' mass with its spin, but that didn't work out very well, mostly because the two weren't as related as we thought. But the eventual idea that came about was that the strings in string theory were absolutely mind-bogglingly small things. They are the size of a Planck length, which if you have seen my video on big numbers or going outside the universe, shameless plug, you'll know that they are supremely tiny. Still, these strings, being purely one-dimensional lines, act much like the strings on a guitar. Imagine each to be taut within the middle of a particle and can only play a single note. Alone, a string makes a pretty sucky tune, but together they make a nice, lovely chord. As they play this tiny ballad, matter acts in accordance to those strings. One of the biggest problems with unifying all of the knowledge we have into one theory is with gravity. Gravity, despite its ability to move planets and keep everything attracted to everything else, is actually the weakest of the four fundamental forces, by a whole lot. So much so that in order to work with what we know so far, we have to pretend like gravity doesn't exist. However, if the graviton, that's the boson particle that causes gravity to exist at all, is real, then we can assume gravity instead works on a quantum level. However, gravity doesn't work that way, which is why strings have to be put in its place. These strings are so tiny that they bump into each other almost without touching. Gravity can't work like this. Finally, Part 3, Application. So now if you're still on board with the incredibly complicated string theory train, you're probably wondering at this point, well, the facts are all there, but what do we do with it? Well, it's not quite that easy. You see, while string theory tries to connect everything to everything else in order to explain how everything works, it's still very flawed. Gravity still poses an issue, and if we include the kinds of strings used in various theories as well as supersymmetry, which regards bosons and fermions as needing an exact opposite particle to exist alongside them, then we have a total of 5 different theories. And these theories are so complicated and convoluted that not only can we not test them, but in order for them to make sense, they need to be shown on higher planes of existence. For example, superstring theories, which make up the majority of string-based thinking, exist in 10 dimensions. Bosonic, on the other hand, requires a whole 26 dimensions. To put it in perspective, our universe exists in 3 dimensions of space and 1 of time. Other matchups of space and time are either too unstable or decay at too rapid a rate to properly exist. So where does that leave us? Well, not very far from where we started, really. As much as we want to explain the universe in simplistic terms, it just can't be done. However, physicists are currently trying to develop M-theory, or the mother of all theories, in which all string theories will be able to be modified and combined to make physical sense. It's a huge undertaking, and as much as I'd like to continue explaining about brains and black holes and all the stuff string theory can be used for, we'd have to delve into another layer of disgusting complication. Thanks for watching, and if you have any questions you'd like me to answer, leave it in the comments or email me at stuffyou'veprobablywondered@gmail.com. Also in the comments, tell me, how long do you think will it take until we've figured out all this mess of complex math and physics to understand the universe? Are there any ideas you can think of that would make string theory simpler? Either way, I'll see you next time on Stuff You've Probably Wondered. Do you have an original song that you've created yourself and are really proud of? Well, email me at stuffyou'veprobablywondered@gmail.com and I'll see if I can include it in the background of my next video.